So let me share my desktop this time. Let me once again try to make a line.
Yeah, same thing. It's just in the very center. There's
okay. So I'll just make sure to draw only on the left part, but you see the text and everything on the right side, right?
Yes.
Okay,
yes.
That's great. So just quick summarization. So just quick summarization for those who will watch this later. When making something from state 0 to plus, we can make it in two ways. First way is through rotation, just to confirm. You see this, right? This arrow and 45. And another way, which we'll learn later, is to make it through projection. Both of these are valid quantum operations, and applying this twice will this operation twice. In case of rotation, which will start now, we'll first transform 0 to plus as we agreed, and then it will transform plus into 1. Similar thing happens when we apply this rotation from 1 to minus, meaning that after rotating by 135, we obtain minus.
Sorry, I don't see this one as well. I mean, just part of that.
Only part of this.
Yes. So when you have 100 something, the angle, we don't see it.
And there's only one you can see.
No, I don't see even one.
If the line ends, but there's like only a about this. This is no. Wait. What your cursor was before was about where the cutoff.
Do you see my cursor everywhere?
We see your cursor, yes.
Okay. So just quick test. Let me say once you stop seeing this.
And I stop.
Okay.
Pavel, Adam, looking on your computer, when there's like 16 line of the code, when there's like 4 in the text, this is like the last, After 4, it's hard. We are not able to see your lines.
Okay, I really don't know what happened. Let me try to follow the suggestion from Rohit and share only my screen, but only my Firefox. Hopefully this will help. What about now?
Yeah, still there's a.
Okay, so one last thing. I'm sorry, but this is really the first time something happened to me. Because I have two displays, which I really hope they could help me, but at the very worst,
Adam, is there a window behind your Firefox, a smaller window that's open?
there's no small window as far as I can tell.
Another program running that has a window.
It appears to be just like a rectangular black zone, the shape of a phone, more or less, in the center.
Can you minimize your Firefox? I think there is something on it.
I'm just quitting with all things.
Adam, it started.
Oh, there we go. No, see, we can see now.
Great. Then maybe it was about some kind of window.
Yeah.
Okay. Sorry for this. Let's just continue. Hopefully they will know the issue again. Yeah. So there is 135 here, 135 here. So very important information you can see already is that applying rotation twice does not necessarily give you back the original state, right? Because we started with 1 and we received -0. Okay, and this rotation gate you saw before can be actually implemented through a quantum gate called RY rotation. R stands from the rotation, Y stands from Y-axis. This is related to the Bloch sphere. We haven't introduced it because this would require introducing complex numbers. But you could see that this RY rotation is exactly rotating along the circle. RY rotation accepts two parameters. First is the angle along which you want to rotate, and there's a qubit on which this rotation is acting. So here is an exemplary code. You can see that this rotation is exactly as this. By the way, you need to multiply angle by twice in order to match the angle as argument of this gate to the angle on this picture. This is again coming from how we represent this rotation on Bloch sphere. Another remark is that instead of using degrees, we are using radians. This is just a different way of writing degrees, and 100 degrees is corresponding to 1 pi radian. If you, for example, want to divide degrees by 3, then you do the same with pi. These are just proportional. When you see that we are rotating by 2 pi 3 over 3, which means that the state will be something like this, we should observe that 1 is measured more often than 0. And this is exactly what is happening. We can also verify this manually, so that the state which came as rotation angle, remember that, okay, I did tell you that before, that Ry, say A, on 1, 0, will give you cosine A. Later I will provide you a formula for Ry. It will be clearer, but this is how you can think of it. That Ry acting on 1, 0 will change the quantum state into cosinus A, sinus A. By the way, if you have now any questions, please just say it to them, if possible, because I can't see chat at this moment.
Earlier question from earlier line of code. In here, when you do the rotationary gate, could you explain? I'm not sure if I missed it. Why there's a 2 times rotation angle?
So the thing is that quantum states, we are showing quantum states as those lying on a circle, right? To be more exact, these quantum states are not lying on a circle, but like on a surface of a ball.
Yes.
And because we are making rotation on this ball, this is why this Y also comes from. It became more natural to have a pi period than 2 pi period. From your perspective, you can simply remember that this is the correlation. Simply that the angle you want to rotate the quantum state, it simply has to always be multiplied by 2. Maybe I can show this actually. Yes, so the surface of a ball is in fact all the quantum states you can have. And the rotation will be from 1 to 0, not on opposite sides of the ball. We just go along this line. And this is exactly this rotation pi. Sorry, actually pi over 2. But you don't have to remember this. This is just extra thing. And going back, if you have cosinus rotation angle, for angle being 2 pi 3, you will have minus cosinus of 2 pi 3, which is, sorry, just cosinus, which is minus 5. And similarly for sinus. And this is exactly what is happening here. Then expected value of observing 0 is just square of it, which is 1 over 4 times 1000 qubits, because we are measuring qubits many times. We are measuring many qubits in such state. So this is how what in real we should observe. And as you see, it matches the experiment. Number of zeros around 0.25, and number of ones is around 0.75. Here you can also write what I wrote before, that rotating around 2 pi 3 will give you this Faust state starting from 0. So we can repeat this experiment for different angle. For example, for pi over 3. Sorry, but something is not right. Oh, wait, it is right. Sorry. So maybe we could have different P over 4. Rotation around P over 4 should give us plus state, right? So we should expect similar statistics. And cosinus of P over 4 and sinus of P over 4 is the same. Square root of 2 over 2. Everything works. Here is a task which you are just repeating the experiment above with different kind of angles. You can choose the random one. But now, as we agreed already, rotations are not the only quantum gates available. Sorry. There are also important gates which are reflections. In the reflections, you specify it represents geometrically through a line. Around which the reflection is made. So there's a very important, you will use this gate later, very important gate Z. Z is very similar to identity, but it works as follows. So Z applied on 0 will produce 0, nothing is changed. And Z applied on 1 is equal to 1, minus 1. Sorry. So you see that if there will be some kind of amplitudes, like for this state, then since square is ignoring the sign, we will get the same probabilities. Anyway, this quantum state is different. And this can be represented on the following circle. If we would have state like this, then since mine z is changing 1 to -1, so it's making a reflection along this axis, then our new state will be like this. So a question now. What will happen if we will apply this reflection gate twice? Say starting from you.
This rotation gate, right?
Reflection. The reflection we were considered so far.
We will get the same state again.
Okay, so so there were many answers. I believe all of them correct. Also, you can see correct answer by Rohit. We'll go back to the original state. And this is true for any reflection we will consider, dependently of this line along which we are making reflection. And it can also be mathematically shown like this. Now, let me erase everything. Perhaps you remember the Hadamard gate, right? We applied Hadamard gate on 0 and we received plus state, right? So it was like H0 was plus, right? And the H plus
we don't see again.
Yes, so we can see again that.
No, sorry, we don't see again what you're writing right now.
You don't. Okay. What about now?
Yes.
Okay, so I know what's happening. It is because of my chat box. So I really just cannot open it because this is the only difference I made. Good to know for the future, and it's strange that this happened. Okay, so back to presentation. Hadamard applied on 0 give plus state. Just to remind you, this is just 1 over square root of 2 at the same below. And applied on this state, it will give you back the 0 state. So now, quick question: is Hadamard gate a rotation or reflection?
Rotation.
It's a reflection, exactly, because applied twice on a state, it will give you the same result as before.
Yeah, but it doesn't define this property doesn't define that this is reflection, right? Because the rotation by just pi also has this property.
Yes, so there are some gates which are both rotations and reflections. I'm trying to figure out an example, but okay, I have an example, but let me show it to you. Okay, I'm not sure if I was right about this. So I think the only case in which this is true is if you have rotation for 180 degrees.
That's true.
No, but that is also not true. Yes, so either this is rotation or this is a reflection. You cannot have both, I think. Unless you can provide an example. Maybe I'm wrong in this case.
So what do you mean by reflection? Because it
Reflection
would be that...
is a geometrical operation in which we are just mirroring the vector with respect to some axis.
Okay, then rotation by pi is also reflection or the line you're reflecting by is perpendicular to you, right?
No, not by pi, because by pi 0 will map to -0, but
but 2 pi, I'm sorry. No, 1 pi is 180 degrees.
But then rotation will map this state into this one, right?
To the original state that applied twice.
Okay, so maybe the definition is not perfect. Okay, so maybe let's just consider. Okay, I need to think about this. I will try to respond better later. Okay, so just please consider it as a property that the reflection gate always works that way, such a way that if you apply it twice, then you get back the original state. This is for sure true. However, you should consider it as a definition. Yes, this is the mistake I made. Sorry for this. Also, let me give you a second. Also, okay. So here you can see that, okay, so this is not mere argument, but anyway, Hadamard operation is a reflection along a special axis. So you can see that it maps 0 to plus and back, as is written here. And similarly, it does it for minus and 1. So from this, you can see that the reflection line looks like this. So that we have here phi over 4. This is exactly how this Hadamard gate works. To test it, actually, to visualize this, it was P over 8, right? P over 4 is plus state, so you need to divide it twice. It's P over 8 along this 0 axis. And that's exactly how it works. So you map 0 into H0, which is plus, and 1 into H1, which is minus. In this task, you can just try with different quantum state, and you should observe the same effect, that this vector will be reflected along with this line. And finally, a little bit harder task is to find a matrix which represents the reflection over y equals x. A hint for you, you already know this state. So it should be relatively easy for you to find this quantum gate, which makes this reflection. So it should be relatively easy for you to find it. Okay, actually, that's a spoiler. So I told you about these two kinds of operations, a reflection and rotation. Let us now go back to rotation gate, which is exactly this RY. This is the only one we know. So, as you remember, we already agreed that applying rotation several times may produce you a different quantum states. Now, the interesting is whether you will at some point receive the quantum state back or not. So, if you have start with 0, you know that you will go to plus. From plus, you will go where? To 1. Then to -1, -0, minus plus, -1, and minus minus. And then minus minus, which is like this, will give you back the 0 state. So you could say that rotation with p/4 angle, in the sense of this circle, at some point will give you the original state. In general, sorry, it wasn't done before. Rotation along this with angle A is taking the following form. Perhaps if you were on some tech studies, you may already saw this rotation gate before. Here we just use the fact that you can also provide a quantum gate with RY rotation, which does the same thing. Note that for p/4, the rotation we already considered, this quantum gate looks very similar to the Hadamard, but perhaps you can see the difference. So Hadamard, let me just take this 1/2, looks like this. So all the values were the same, except in absolute value, except that this minus, instead of being on top right, for Hadamard it's on bottom right corner. So you can see that even such a small change may lead to a very different behavior of the quantum state.
So the Hadamard gate, is it a reflection? Because certainly it's not rotation matrix. So it's not a rotation operation.
For here, all gates will be either a rotation or a reflection. I think if I didn't tell this before, then let me just take it one more time. Along this axis, oh, here it is. This axis, which has slope, which is the angle between this axis and 0 axis is p/8. And this very similar quantum gate, which is not a Hadamard, is an example of rotation with π/4 angle. Was the explanation clear, or should I explain something? Don't hesitate to ask if you have problem with anything. Okay, let me just quickly check chat. Okay, so Keshav asked, I'm not sure if Keshav was the one who asked, that's right here. A Hadamard can be a rotation, no, it is a reflection. It is said, yes, and Rohit just gave an answer. Great. Let me just turn off this chat, just in case. So here you will be able to see the effect I told you before, that after several times you will just go back to the original quantum state. And now, interesting technical mark. Previously, when we had a quantum circuit, we were receiving some statistics of 0, right? So it has like 0, say 1000, and 900. Sorry, 100 and 900. And this is what you should expect from quantum computer, only this kind of statistics. However, if you run this quantum circuit on a classical computer, you can have a little bit more. Inefficiently way, usually, but anyway more. So for example, using a different backend of AER, you can actually get the form of the state vector, the vector which represents the quantum state. It will output you a complex number in order to get the real part. You just need to add this. This is the technical but important detail. What's important to remember is that getting such kind of information, like the exact form of a quantum state, is not possible on a quantum computer. In a few minutes, I will show you that this can be approximately done, but only approximately.
Could you please explain that again?
Sorry, there was a question, but you were extremely quiet. Perhaps you could write it on chat.
Could you please explain the last part again?
So I should explain something, but what exactly?
Using state vector simulator instead of QSM simulator, you said it will do something different.
So exactly, QASM simulator will give you the statistics and state vector will give you the state. For example, I don't know, 1 over square root of 2. So this could be an example, right? If you will have circuit like this. So only apply Hadamard. State vector will give you the actual ideal quantum state, but this is not physical. This is not how quantum computer works. And QASM will simulate the quantum computers and give you statistics of getting zeros and ones, which is exactly how quantum computers works right now. Okay. So here you can, with this task, you can use the state vector simulator to find out the state after each rotation. To just convince yourself about this path we made here. 0 to plus to 1 to minus 0 to minus plus to minus 1 to minus minus and back to 0. This is okay. So this is the actual form which I presented to you before. You see that there is this minus, which is messing up. Which is making a problem why this is not why you can make it a Hadamard matrix. And finally, there's a very interesting task free in here, in which you can do the following. You can run this and this experiment, but let's find the rotation square root 2 of pi. I recommend you to work on this example, but let me just show you results. So for p over 6, you see that we are going back to the original position 0. For 3 pi over 8, we also have the same situation. But for square root 2 pi, you see that there are some spaces in here. In fact, we can do even more. For example, you can make it 200 times, and you can see, okay, this looks terrible, but you will just observe some very, very, very dense collection of arrows. In fact, you could say that choosing such angle will never allow you to go back to ideal zero state. And this, what I just said, is related to this discussion. So the question is, if we choose this parameter alpha, which is next to this 2 pi or pi, that actually that doesn't really matter. The question is, for which kind of alpha the zero state will be revisited at some point. It may be many steps, but it will be, ideally. And for which alpha it will never be visited. Okay, so this is not a very simple question, but perhaps some of you knows the solution.
For measurable numbers, I'm not sure the exact word in English, but they cannot be defined by division of another two numbers.
Mm-hmm.
I think for rational numbers, it will visit the zero state, and for irrational angles, I should say, it
Exactly.
might not.
So the thing is, at least for rational, it's extremely difficult, extremely simple to show. Suppose we have a rational number p over q. These are integers, both p and q. We just apply this rotation gate q times, and you are guaranteed that this angle will be 2 times pi times this p. But cosinus of 2 times pi times p, here will give you 1, 0, 0, and 1. So this will be an identity matrix. So after q, maybe sooner, but at least after q, we will visit 0 again. Unfortunately, I cannot prove this for irrational number right now. I guess this proof will be much more complicated. Basically, it could suffice to show that for any integer k, actually you can solve it. Okay, so what you would need from this? You would need that for some positive k times alpha is rational, right? Or actually you can even say integer, right? Because if you can make it rational, then you can just multiply by q and you will have integer. But if k alpha is integer, say p, then p over k would be rational. But we just assume that alpha is not rational. So we get a contradiction. So for irrational numbers, 0 will never be visited. This proof is tricky. If you don't understand it, don't worry. You can also ask me later on the after the lecture. But this is interesting to see that we actually can quite nicely describe alpha for which one or second scenario happens. So there are 2 more tasks. This is a relatively simple task, so I don't want to talk about it too much. but let me just describe this one. I don't want to provide you solution, but I will give you a hint. So you are rotating 0 either θ1, sorry, or θ2 minus P2. P2 is 19 degrees angles, right? Another question is, which state you get? The question is whether you can do this with a single measurement result. You know this theta, you just don't know which of these θ1, θ2 was chosen. So the question is, with an appropriate rotation θ prime, can you make a single measurement which will clearly tell you which of θ1 and θ2 was used? Okay, so this may be not an immediate task to solve, but perhaps some of you have know the answer already. If not, I will not give you a spoiler. As always, you can find your solution in the solution notebook.
Would the rotation be pi? Means
This one?
if we rotate it by pi, we would get back to I mean twice the pi would give it the original state.
In twice pi? 2
yeah,
pi?
2 times. Yeah, 2 pi.
2 pi rotation will make one full circle, so we'll get back to the state as previous. Essentially, this has no effect on the quantum state, 2 pi rotation. We need to choose different rotation.
Sure.
I can already tell that this rotation will be related to theta. But okay, please consider this as a task for you. And now let's go to something probably far more interesting for you, which shows you that I a little bit lied before, but only a little bit. So previously I told you that if you will have on a quantum computer a general qubit alpha beta, okay, maybe it's not there, then it's not possible to get the form of the quantum state exactly. This part was true, but we can simplify this. We can approximate this. So suppose we have a classical state, like P1 minus P. So perhaps solved the task before. How can you derive value of P if you have many bits around this distribution? You can take number of zeros and divide it over the number of all samples, right? Then if you will have 100 zeros out of 10 samples, then you will have 100 over 1000, which is 1 over 10, right? So this is only an approximation of the ideal value P, but the more samples you will have, the more exact this approximation will be. So suppose now we have quantum state. Right? you know that any quantum state needs to satisfy this equality. Can you provide a method of computing alpha and beta given many samples 0 and 1s?
There isn't a single solution.
Sorry?
There isn't a single solution, is there? Because of the squares.
So yes, if I understood you correctly, you can use exactly the same method. So alpha squared is number of zeros, because these are probabilities, right? They are not amplitudes anymore. So this is number of zeros over number of all. By the way, hash zero, by hash zero, I mean number of zeros. This is a computer science nomenclature. And if you want to learn the value of alpha, then what we do, we just take a square root of it, right? Since we get the value of alpha, then we can derive.
How about
Yes?
the case that when alpha is negative?
So I'm going right back to it. So, okay, so first of all, alpha beta is plus minus this function, and beta is plus minus 1 minus alpha squared, right? This is taken from the formula above. So, up to this plus minus, are there any questions about what I presented? Okay, if there are no questions, then let me just first present you a task, how to solve it. Actually, how to understand this, right? Because maybe understanding is a little bit more difficult than solving. But we will assume for the moment that all of these elements are non-negative. This is just assumption for now. Later we will deal with this as well. So we will create a unknown qubit. We specify the number of qubits you want and the angle. So for yourself, you can start with some simple angles, but later you can just try random angles as well. It will be a little bit more fair. And then you can measure the qubits. Sorry, I didn't compile previous cell. So it created 100,000 qubits. You created a qubit with angle like this in radian, and you get the following statistics. This is the statistics coming from pi over 3. Here you can test your solution. Which apparently is not working. Oh, excuse me, sorry. It is generating a random rotation for you already. It just won't show it for you. And the task is to guess it using the procedure above with some extra things, which I will tell you later. This function will be important later about exactly this sign. So there's a problem as one of you mentioned. Suppose we have those two very simple states, right? This is a plus state, this is this minus state. So the first thing, using our method, you will have a problem with choosing sign here and here, right? But you can approximate the module of the absolute value of the amplitude, which is already very good. Basically, we have only 4 possibilities: both plus, both minus, first plus then minus, and first minus then plus. So how these states will look like? It will be this, 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 and this, right? So it will be always all the possibilities reflecting along the ket0 state and ket1 state, right? So how you can check whether, let's first focus on these 2 states, okay? What we can do, since we know both of these possibilities, we can take the one with smaller angle and rotate it along the alpha. So after rotation, you can do through this method, you will have 2 possibilities. Either this is 0, or this is some alpha 0 plus beta 1, right? Now, what you do is that you are measuring it. You are measuring it, and now if all of your outcomes will be, if at any time you will get outcome 1, then since you can't get 1 from this, it means that this state is for sure this one, so originally this one. If you won't have 1, then with very, very high probability, it means it was this one. You see the procedure here. Perhaps you have some questions at this moment.
I didn't quite get it. Can you do it one more time? Try to explain this.
Okay.
Can you repeat this?
Sure. But do you understand how to get these amplitude values, alpha, beta, up to sine?
Yeah.
Okay. Do you see that these are 2 out of 4 possibilities?
Yes.
Great. So we know how to apply rotation rate, right? So we are rotating this so that we can get one state.
But what are we rotating?
The quantum state. The quantum state which we know is this or this. So then we get this or this. We don't know which one. We just know it is one of them.
Yeah, I know, but the quantum state we can have it in four possibilities, right? There are four possibilities to rotate.
Okay, so now we just assume we are trying to check whether these are one of these 2. This was the assumption I made at the very beginning. Apparently, this is a justified assumption, but I will tell about this later. But supposing that we know that this is one of these 2, do you see how to make this operation? If you don't, then please just say it. It's also important to know for me if I can proceed. What you do is that you just take this alpha, beta, and you know that alpha is cosinus of angle A, right?
Right.
So A is cos inverse of the cosinus. It is a cosinus of alpha. So you are rotating by minus alpha, these vectors.
But the A cos, there are two solutions, right? Because
if you know the alpha beta, then you know that this is one of these four. Right now we are dealing with these two things. And we assume that this is one of these two.
yeah, but from what domain the alpha is when using
alpha? You already know. Alpha and beta is so you take the ones which alpha and beta are positive, are both positive.
Okay.
So this way, one state will be ket0, and one will be this alpha prime ket0 plus beta prime 1, right? So what are the probabilities for both states of getting 1? Here this is just 0, and here this is something close, something positive, right? So if you will observe 1 here, then it means that this was the original vector. Otherwise, if you will have only 0, or because this A is known imperfectly, you have very tiny number of 1s, then it means that this was the original quantum state, right? So provided you know that one of these are correct, you know how to tell which one it is.
I think the number of ones that we get after measurement should not be important. The moment we get, even if a single one, we know that it wasn't the first state.
Okay, so you would need, sorry, could you repeat because you were very quiet?
Yes, I'm saying that the number of ones that we get after measurement should not be important. The moment we get the first one, we know that which state it is.
This will be perfect if you would know this A exactly. But this A, you know only, this A is taken from alpha, right? And this alpha you know imperfectly.
Okay, yes.
So also this 0 will be actually something very close to 0. So if you make a lot of measurements to derive these values alpha, beta, then likely you can just safely follow your own procedure. True.
Right.
But if these numbers will be small, which I don't recommend for this experiment, just take like, I don't know, thousands of experiments, then you can really, if the number of measurements is large, you can just take the first one. If it's small, then you may prefer to check the how frequent is this one. So this is like a distinction between ideal and approximate scenario. Okay, for this task, I strongly recommend you to use a lot of measurement. In fact, I think there were proportions like 900 to take alpha and beta, and 100 for getting the sign. Okay, so this is extra task, so maybe not focus. Let us not focus on this for now. But now let us complete the procedure, because we made a very heavy assumption. before we already agreed that we have 4 possibilities, right? In each quadrant. So we were assuming that both were up, you could say, that were both positive, or for 1 it was positive and for 0 it was negative. In fact, you can choose these two, this doesn't really matter. But let us go to a, you could say, realistic scenario. What if we should consider all of this? So note that the difference between this one and this one is in the sign. Means that you have alpha, beta. Right now they can be positive, negative. And minus alpha, minus beta. So it is like ket v and minus ket v. What will happen if we apply some quantum gate on it? Then it will be just like for the first one, and this minus will go. We'll just pass through it. At the same time, if you would make measurement, then we already agreed that this minus doesn't matter at all. What does it mean? It means that there's no difference, no physical difference between these 2 quantum states. To be more exact, there's no way of transforming the quantum state or measuring it, which could tell you whether you have this quantum state or this quantum state. And this minus sign, well, if we would use complex state, it could be any complex number with the module 1. It's called a global phase. This is to distinct the local phase, which is just the sign next to the amplitude. And it allows us to just forget about these 2 possibilities and focus only on these 2. So the procedure we had before just works like this.
So we are getting from 4 states to only 2 states because.
Yes. So first, by deriving alpha and beta, we just reduce ourselves to 4 quantum states, you could tell. But then, thanks to this global phase, you can get rid of this other 2. But remember that this global phase is something more general than for this tomography. It's always true that if you have states alpha, beta, and minus alpha, minus beta, the state will be always the same. And there is also a short explanation about global phase in here. Okay, so because that's all about the quantum tomography. Unfortunately, we don't have much time for questions, and there are still 2 notebooks. So let me just proceed. I'm terribly sorry for this. Please keep in mind you can always ask on Discord. But let's now go to the 2 qubits operation. So you remember that previously we could have 2 bits, and these bits could be correlated and NOR. 2 states, 2 qubits. Sorry, not how. 2 bits with given stochastic vector could be connected with a Kronecker product which would give you PR, T1 minus R, 1 minus PR, and 1 minus P, 1 minus R. Since we can write this in this form, we can say that these stochastic vectors or the random variables according for this bits were independent. And the same as previously, the deterministic states were 0, 0. So I'm not sure if this was exactly the parentheses we were using. We have exactly the same basic states in the quantum. Simply their meaning is different, because here it was a probabilistic, a stochastic vector. Here it is just a quantum state. But anyway, the probabilities of observing each of these labels will be the same. So your next task will be to generalize this idea. This is a very simple thing into the one in which you have many qubits. A hint for you: k qubits, and actually this is the same for bits, will mean that you have vector of length 2 to the k. Now, obviously, if you have many qubits, you want to also apply many operations of it. So, for example, we already did this before with a NOT operator, but we can also make it with other 1 qubit gates, like Hadamard. So here we have 2 qubits, on each we are applying Hadamard gate, and the same as it was for a vector, the same you are merging these operations. So just take first matrix, second matrix, and apply Kronecker product. To visualize this for you, this will just be A11B, A12B, A21B, A22B. If you will replace this B with this matrix, then you will get exactly matrix of this form. And finally, you can take this matrix by running another simulator, which is also not physical, which is called unitary simulator. There's one thing, there's a mistake in the code. Here there's missing that data. So please remember when you will check this unitary matrix that you should add this. Okay, so there's just tasks for you to convince yourself that you know how this Kronecker product works. And what is also interesting, it is to understand how in a different way you can apply, we could say, multi-qubit gates on qubits. So one way, the very naive one, is that you just take this Hadamard applied twice, applied to 2 qubits on 0 state. Just take this enormous matrix and multiply it by this enormous vector. I'm saying that it is enormous now, but well, this has only 4 and 16 elements. But if you would take 3, 4, and more Hadamards, then this will increase a lot. However, note that these are 1 qubit gates, meaning that these are Hadamards applied on each qubit. So instead, you can just split this Hadamard and write it with this notation. So it's Hadamard on 0, tensor Hadamard on 0. These are these 2 plus states, and using the formula for Kronecker product, we get the same output. Finally, there is, I would say, most pleasant way, where you just, instead of writing vectors, you are using this ket notation. And remember that this, you could say, works a little bit like in polynomials. So you multiply this by this, so you have 1 over 2, 0, 0. This by this, so it is 1 over 2, 1, 0. 0 by 1, so 1 over 2, 1, 0. and this by this, which is 1 to 1, 1. And this, obviously taking this form of basic vector, will give you the final one. Here there are just many different calculations, which are exactly the same as above, but are in a different input state. 0, 1, 1, 0, and 1, 1. I definitely recommend you to try yourself and maybe for the first time, consider all these methods, write this, for example, on the paper. And then compare your results with the one which you will get here. But obviously, it will be extremely boring if we could make only 1 qubit operations. Why is that? If circuit will only consist of operations that act on a single qubit, then you could say that each qubit is being changed independently. So it's like you can just spread all these qubits along the world, and there were simply no interactions. Similar thing would be boring even for stochastic, for probabilistic evolution, for stochastic matrices. So what we need is the quantum gate which puts a correlation between these qubits. So an example of such gate is a CNOT. CNOT, you could think it is a classical gate, which works like this. It checks what is the value of the first qubit, and if it is 1, then it changes the value on the second qubit into the opposite one. You can try yourself how control X works by checking this code. Here there are just different combinations of the input state. So exactly it is just Qiskit version of what is written here. And finally, there are some more tasks, out of which 6 and 7 are extremely interesting. So I would say something extremely terrible, meaning that the CNOT is a classical gate. Obviously, it is quantum gate, but meaning that it works very classically, meaning that it changes only the labels of these basic quantum states. This always happens when these gates consist only of zeros and ones in their matrix representation. And there are 2 very interesting circuits provided by task 6 and task 7, which shows that by very specific quantum gates, local, like here it's Hadamard, you can swap the direction of how CNOT acts, like from the second to first, will be from the first to second. By the way, I forgot to mention this, sorry. CX is implemented like this, when here it is target, and here it is a control qubit. And it is visualized like this. Dot is always a control, and this plus is a target qubit. Sorry, because it's reversed. That's why I was confused. So this is a control, this is a target. Because this is 1, so it's Q1, and this is 0, so it's Q0. And here you should observe that the control and target are replaced with Hadamard gates. We'll also talk about that a little bit in a minute. And finally, by applying a sequence of 3 CNOTs, you will see that the bits values will be swapped. I also recommend to take the unitary and see how it looks like, thanks to this unitary simulator I showed you before. Okay, there's a time for one very quick question. Okay, so one very important fact, using this CNOT gate and any 1 qubit quantum gate, I mean that all these 1 qubit gates are allowed, it is possible to generate absolutely any quantum operation you could think of. Okay. So, in the last notebook, I will show you something extremely strange. Something which is called phase kickback. So, suppose you start in a state 1, 0, and you're applying not like this. So maybe let me just quickly hide this. So what will be what will be measured on this and this qubit? Maybe use the name top bottom qubits. Remember, this is control, this is not, and you always start from 0. Is there anyone who could provide an answer? So after this node, it will be 1. Because this, sorry, right, just too fast. 0, 1. Nothing is changed because this could be 0. So we will always get 0, 1. And it matches the count we observe. But what if we will apply Hadamard like this? So you remember that previously it was 0, 1, but now it is 1, 1. What happened, which is extremely strange, and is very natural to quantum computing. So despite the fact that we were changing only this qubit, and that control was made in here, we also changed the qubit, we also changed this qubit from 0 to 1. Why this is important? It means that when you're applying a CNOT and you have something called control and target, it doesn't guarantee you that the control qubit will not be changed as well. This phenomenon will be used later in Grover algorithm in this course on Friday. Here there are just a detailed derivation, step by step, what happened. So there is a little bit time, so let me just quickly go through it. Tasks here are very simple, fortunately. So if we start in 0, 1, based on Hadamard, we're getting plus and minus, and this is the joint form. And taking 0 and 1, taking 0 times this and 1 this, you can have exactly the same representation in here. There are no gates applied yet. This is just reformulated. When you apply NOT, then you see this is the target qubit, so nothing is changed, and this is the target qubit, so we swap 0 to 1, and 1 to 0. But this is the same state as this, except of this minus. So we can just take minus before and keep the same formulation. And this will give us, apparently there is. Again, after simple algebraic manipulation, you will get this sign back. This state is minus minus, which after applying Hadamard's will give you 1, 1. So both Kiskin and maths agrees, and this is in fact how quantum computer can work. Finally, there's just a simple task to convince you about this phase kickback phenomena. This is the name of the phenomenon we just saw here. And this is all I wanted to say for today. As usual, I would like to convince you with the questions. Right now, I see only comments from Rohit, Gupta, and Damian, but this was about this notebook from the rotations. So I guess these questions are already solved. But are there any other questions? You can now write also on chat.
Just, I guess, as a refresher, because when we have the visualization of the C0 gate, the dot is the qubit that we check is 1, or if the dot is the qubit that we change.
Okay, so I guess I should be a bit more careful about this. This is control. And this is target.
You have the chat box open again.
Sorry. No, this is disastrous. So, control, naturally speaking, you could say that control is the qubit based on which the target is changed.
Okay. Okay, just wanted to make sure.
Sure. Thank you for this question. Are there any other questions? If you are not sure about the question, then obviously I recommend you to write this question on Discord later, unless you want to say it now, but you can also write a direct message to me on Discord. Okay, so if there are no questions, then thank you for coming today, and see you tomorrow, 5 p.m. Polish time and 4 p.m. Irish time. Thank you and goodbye.
Bye.